Welcome to the video lecture for section 3.3. This is for statistics, STA 2023. My name is Jorge Gabriel. So we're going to be talking about measures of relative standing and box plots in this lecture. So in this section, we're going to introduce measures of relative standing. We've talked about measures of variation and also measures of center. And measures of relative standing are numbers showing the location of a data value in relative to other data values within the same data set. The most important concept in this section is the Z-score. We're also going to talk about percentiles, quartiles, and Boxplot. So a Z-score, or standard score, or standardized value, is the number of standard deviations that a given value x is above or below the mean. Now the Z-score is calculated using the following. So if we have a sample, we use the formula on the left. If we have population, we use the formula on the right with the corresponding symbols. We always round Z-scores to 2 decimal places. So some important properties. Z-score is the number of standard deviations that a given value x is above or below the mean. Z-scores are expressed as numbers with no units of measurement. A data value is significantly low if its Z-score is less than or equal to -2, or its value is significantly high if the Z-score is greater than or equal to +2. If an individual data value is less than the mean, the corresponding Z-score will be negative, and the opposite is also true. So here's an example. We're going to compare these two, a 4,000 gram weight of a newborn baby to a 99-degree Fahrenheit temperature of an adult. So the 4,000 gram weight of a newborn baby, the sample size was 400 with a sample mean of 3,152 grams and a sample standard deviation of 693.4 grams. The 99-degree Fahrenheit temperature of an adult, it's 100 sample size of 106 adults, sample mean 98.20 degrees Fahrenheit, and a sample standard deviation of 0.62 degrees Fahrenheit. So we plug these into the formula, and we get 1.22 for the birth weight, we get 1.29 for the body temperature. Now the Z-score showed that the birth weight is 1.22 standard deviations above the mean. The body temperature is 1.29 standard deviations above the mean. Now because the body temperature has a higher or greater Z-score, it is further away from the mean than the birth weight, and so therefore the relative standing, the body, a 99-degree Fahrenheit body temperature is a higher value, if you will, in comparison to the other values that the birth weight is in comparison to one within the data set of itself. I don't like to use the word extreme because honestly a Z-score of 1.22 or 1.29, that's within plus or minus 2, so that's not really extreme. Compared to each other, one is greater than the other, but I wouldn't use extreme. And so just to recap, anything below plus or minus 2 standard deviations from the mean are considered significantly low or high. If it's within plus or minus 2, then it's not considered significant at all. Now here's an example, platelet count of 75. Is this significantly low? And so the lowest platelet count in the data set is 75. Now this is measured in units of 1,000 cells. Now is that value significantly low? So we're going to assume that the platelet counts have a mean X bar of 239.4 and a sample standard deviation of 64.2. So when we find a Z-score, we find that the Z-score for this particular data point is negative 2.56. And so the negative 2.56 means that it is in fact significantly low because it's below -2. And so again, within plus or minus 2, it's not below -2, above +2 it is. Next thing we're going to talk about is percentiles. Now percentiles are measures of location denoted by P1, P2 to P99. The highest you can get is a 99th percentile. That means you're above everyone. So percentiles divide a set of data into 100 groups with about 1% of the values in each group. Now, how do we find the percentile for a specific data value? So we take the percentile of a value x is equal to the number of values less than x divided by the total number of values times 100. And so here in this data set that we've used previously, we're going to find a percentile for percentile rank, if you will, for 11.8 megabytes per second. And so the way that we find that is we figured out that there's 20 values less than 11.8 divided by 50. Those are the total number of data points times 100 gives us 40. So then a data speed of 11.8 megabytes per second is in the 40th percentile. What does that mean? That means that it separates the lowest 40% of values from the highest 60% of values, and so P40 is 11.8 megabytes per second. So let me show you how to find that in Excel. And so if we go to 11.8, we can actually find that by using what they call percent rank, and we want to use the EXC. So we just simply highlight the raw data first, and then the next thing that we want is the actual data point, and in this case I want this one right here, and then I press enter. And so if you notice, if I use the .exe, I get 0.411, and then if I use the INC, and the reason I'm showing you this is you're going to see when we go back to find the 5-number summary that Excel is a little glitchy. And so what do, right? I mean, if I were to round this, it would be the 41st percentile for either one of them. This is what the textbook got, a 0.408 as opposed to a 0.411. And so you have to make a decision. I prefer that you use the INC. I think it's closer to the actual rank, and it's a faster way of you finding the percent rank of a particular data point. So that's just the key difference between those two. The details of why they're different is just a matter of the algorithm that they use, but let's just use a .inc for our purposes. And so there is some notation. Lowercase n, again, is the total number of values in a data set. K is the percentile being used, right? L is the locator, which gives the precision of a value. And then pk, the kth percentile, is, p of 25 is the 25th percentile. And so I'm not going to go through this whole list here, converting a percentile to a data value. You guys can read this. Really don't assess in any of this. It's just a way of finding out what's what. Now, if you look at this particular information here, they're saying that the 40th percentile, and they go through this, we get 20, right? So it's a 20th spot location for the 40th percentile. And so in this particular one, it's saying that it's between 11.6 and 11.8. Now, we found out that 11.8 is actually the 40th percentile, the 41st percentile, if you will. But here's a quick way for you to find out what's what within a data set. To be honest with you, real life, we don't really do this. But it's just nice a way to either find a percentile rank or the percentile of a data value. Next thing is quartiles. Now, quartiles are measures of location, denoted by Q1, Q2, and Q3. Q2 is simply the median, and this divides the data set into 4 groups, 25% each. And so, again, you get Q1, Q2, and Q3, so you get 4 slices of the data set. Quartiles come into play when we calculate the 5-number summary. So the first quartile is the same as the 25th percentile. Second quartile is the same as the median. Third quartile is the 75th percentile. Now, just as there's no universal agreement on the procedure for finding percentiles, there's not a universal agreement for a single procedure for calculating quartiles, and different technologies often yield different results. That happens, and you're going to see that when I show you something in Excel in a few minutes. Some of the things that are important: interquartile range. Out of all of this is the most important one. IQR is Q3 minus Q1. Remember that. Everything else is nice to know, but we really won't go into any of those other values. And the reason why IQR is important is because it allows us to find outliers. It gives us a mathematical way to find outliers, as opposed to saying, hey, that looks like an outlier. So the 5-number summary. 5-number summary for a set of data, the 5-number summary consists of the following: the minimum, the first quartile, Q1, the second quartile, Q2, or the median, third quartile, Q3, and then the maximum. And so that's your 5-number summary. It is an important aspect of descriptive stats and also allows us to build the box plot. So we're going to use this information to go ahead and build the box plot, we're going to find this 5-number summary for this particular data set. So the min and the max, easy to find, right? We just order them, we find those values. The median, right? That's an easier way to do to find. Q1, what Q1 does is that it is the median of the first half of the data set. Q3 is the median of the second half of the data set. So the median divides it into 2 equal parts. Q1 is the median of the first part, Q3 is the median of the second part, if you want to think of it in that way. Now look at these values that we got here. We got 0.8, 7.9, 13.9, 21.5, and 77.8. And so before I go to Boxplot, I do want to show you something. So if I find these manually, I got my minimum, right? I got my maximum there, which is pretty straightforward. I didn't even have to use the formulas because I ordered them from smallest to largest. Now, if I had not done that, this would have been a quick way for me to find those values. Here's my median, quick and easy. And then my Q1, that's the formula that we use for if we're doing it by hand, not by hand, but using this particular function. We use the quartile.exe, and you notice that it has 2 components to this formula. The first one is the raw data, and then the second one is the quartile that I want. And then if I look at Q3, the only difference between the Q1 and Q3 is the last value, which is a 3 as opposed to a 1. And so this is my 5-number summary. And so if I do it like this, I get the same values that I got in the lecture. Now, if I use Megastat, let me move this over a little bit. If I use Megastat, it actually gives me different values. And I'm going to show you what that looks like. And so if I go to descriptive stats, my input range is my raw data that we've been looking at here. And so I want these values right here. I don't need those 2. And we'll come back and do the box plot. But if I click OK, and then if you notice, it gave me my min, gave me my max, right, which is 0.8, 77.8. My first quartile was 8.4, and then my third quartile was 21.4 with my median of 13.9. And it did give me my interquartile range, my IQR, which is 13, which is good. It also told me, hey, you have 2 outliers and 2 extreme values, right? And then when we construct the box plot, we're going to be able to see those. And the difference here is that in this one, we used the EXE. Now, if I were to use, oops, not that one. I want this one. If I use this one, right, and then I want the first one, it gives me the 8.4, and that's a key difference. So the difference between the INC and the EXE is that you get a different value pretty much. And it goes back to the algorithm, how they calculate it. But just like the textbook said, there's no set way. Using different software, different technology might give you slightly different values, and it's okay. And the same thing for here. If I were to do the I think that's the one that I used the first time. Hold on a second. I get confused. I apologize. Oh, yeah, not that one. And you can see that I get a different value. I actually get the same value that we got using Megastat. And I got 21.4. And so whichever way you do it, it doesn't matter. If you use the output, either one is okay. I'm not going to be grading you on the specifics of how you calculated those values. And so the next thing we're going to talk about is box plots. And a box plot is simply a graph of a data set that is a line consisting of the min value, the max value, Q1, Q2, and Q3. And so if you were doing it by hand, you would follow all of these, instructions, but 21st century, we use technology to construct these for us. And so using the same data set, we get this box plot. Now, the one that I'm going to show you in a moment is slightly different than this one. And the reason being, Megastat does give us those outliers and those extreme values, and then I'll point those out when I show you that particular box plot. And so, let me go back here. So if I want to do a box plot, I go back to descriptive stats. I click on box plot. I don't really need any of those values. I click on OK. And then you're going to see that it is slightly different. So this is similar to the box plot that they have, sort of. Here are your outliers, and these 2 points are considered the outliers. These 2 points are considered the extreme. And so, honestly, I would just call them outliers, and there is a way to calculate those, and we'll learn that later on in the course. But basically what you do is you take the IQR, you multiply it times 1.5, you subtract the Q1 from that value, and then you add it to the Q3. That'll give you an interval. And anything outside that interval are considered outliers. And that's a mathematical way of confirming if a data point is in fact an outlier. And then the last thing, well, there's a few other things that I want to talk about, but skewness. A box plot can also often be used to identify skewness. So distribution of data set is skewed if it's not symmetric, if it extends too much to one side as opposed to the other. And this is how we identify outliers. So we find the Q1, Q, and 3. We find the IQR. We're going to multiply 1.5 times the IQR. If a data value is an outlier, if it's above Q3, so you're going to add this value to Q3. And you're going to subtract that value from Q1, and anything outside those parameters are considered to be outliers. Modified box plot, that's what I showed you, special symbol, asterisk or a point to identify outliers. And so you were able to see that in the one that Megastat creates. And before that's the end of 3.3, I do want to show you one other thing. So here's those data points, this data that we've been working with. We talk about standard deviations. And so when I went back in, we found here's the mean of this data set, and here's the standard deviation. That's a huge standard deviation compared to this. And so I kept talking about in context. What does it mean? When I see something like this, I immediately start thinking, wow, that's a lot of variation. And so remember, the mean is 17.6, so the standard deviation is 16.2. So 16.02 is the average distance these points are from this red line. This red line right here is your 17.6, your mean line. And you can see that the points are actually quite a distance away from this particular red line. You got some all the way down here, and then of course these are pulling up that standard deviation quite a bit because they're really far away from this red line. If this standard deviation was smaller, let's say 10 or even 8 or 7, these points would be a whole lot closer to this line. If the standard deviation would be like a 4 or a 3, I mean, these points will almost be in a straight line right around this red line right here. So when you look at standard deviation and the mean, if those two values are almost the same, or the standard deviation is greater, if you were to plot it and then plot the mean line, these points would be all over the place. I mean nowhere near the red line. So that's just the last point that I wanted to point out before I ended 3.3. Thank you.